Hi Year 13. We're going to do a nice super easy peasy lesson today. This was the chapter 4 in the S1 book that I was talking to you about, which is basically correlation that we already know from GCSE. A little bit of new stuff from regression lines, but we can do the whole of chapter 4 in one lesson. So that's what we're going to do today, the whole of chapter 4. So when it comes to practice, you can do a bit of 4A and 4B. If you want to, you can go straight to the mixed exercise, okay? Pick out a few things, just make sure you know everything which I'm going to go through today, okay? So previously, we've only considered one variable at a time. When we introduce a second one, for example, height and weight, we might want to consider the relationship between them. This is known as bivariate data. So bivariate data is data which has pairs of values for two variables. And you've studied this both in Key Stage 3 and Key Stage 4 by using a scatter diagram. So a scatter diagram has got one of your variables on the x-axis, the other one on the y-axis. You plot little crosses, not points, but crosses, okay? And then you look at the shape of them. So here we can see from the shape of these points that the more breaths per minute, the more pulse beats per minute. So as one gets bigger, the other gets bigger. So it's showing positive correlation, okay? So it's the shape of the points that's important. So positive correlation is as one gets bigger, the other gets bigger. Negative correlation indicates that as one gets bigger, the other gets smaller. So something like the age of a car and its value. So older cars are worth less, younger cars are expensive, and stuff in between. That would give you negative correlation, okay? So the two different variables in a set of bivariate data are often related. Sometimes they're not, sometimes there's no correlation. And then we've got here examples of a weak positive, so they're not quite so tight together, the points. The more they form a line, the stronger the correlation is. Okay, so strong positive correlation forming a nice line. Weak positive, kind of together, but not as liney. Okay, no correlation all over the place. Strong positive, strong negative, because it slopes that way, weak negative. Now imagine I was going to put those onto a probability scale, okay? So here is 0, which means no correlation. Here is 1, which is perfect positive. And here is -1, which is perfect negative. And if you've ever done this in a spreadsheet, you can get it to examine some bivariate data, and using your correl function, you can return a value. That value will be between -1 and +1 with this interpretation. So in terms of what's strong, really works out around about 0.7 onwards, you consider to be strong, and -0.7 downwards, you'd be considered to be strong negative. So these are probably strong. Perfect positive would lie exactly on a straight line. Perfect negative would lie exactly on a straight line. So these are more sort of somewhere around here. All right. So this idea of going from -1 to +1 with 0 showing no correlation, I've jumped the gun a little bit because I come on to that in a minute when I talk to you about the product moment correlation coefficient. So I'll hold my horses on that. Okay. So on to the next page. Very easy. Probably don't even need to do it, but just humour me. So here we've got some sort of weak positive correlation. So when you're asked to describe the correlation, you're looking at its strength and its type. Okay, and this one will be a weak negative correlation. This one will be a strong positive. And this one probably shows no correlation at all. Okay, now this bit down here is really important. So this is something you must remember for today, which is some vocabulary. So the vertical axis, the y-axis, the thing on the y-axis depends on the thing on the x-axis. Okay, that's how we plot it. So this example was weekly time on the internet in hours on the y-axis and your age, okay? So the insinuation is that this is the thing which you fix, your age, and then the thing on the y-axis, how long you spend on the internet, is dependent upon your age. So the words that we need to remember here are independent or explanatory variables versus dependent or response variables, okay? So use those words as pairs. So this is the independent variable and this is the dependent variable, or it could be described as this one being the explanatory variable and this one being the response variable, okay? So either pairs of descriptions, don't mix them up. Okay, important correlation concepts. Obviously, if I'm going too quickly, just pause me so that you can do your notes, all right? So important point 1, to interpret the correlation between two variables is to give a worded description of the context of the problem. So state the correlation, I'm looking for strong, weak, positive, negative. Interpret the relationship, I'm looking for wordy answers, okay? So in this question, we've got it's that one again, age and number of hours on the internet. So state the correlation shown, well, it shows weak negative correlation, and describe it. So the older you are, the less time you tend to spend on the internet. Yeah, we can see that because we've got the youngs doing loads, lots of time, we've got the olds doing less time. Okay? Important point 2. Right. This is about whether or not two variables have a causal relationship. So they do have a causal relationship if a change in one variable directly causes a change in the other. Now, just because two variables show correlation, it does not necessarily mean they have a causal relationship. So what you need to remember is that correlation does not mean causation. Okay, so one might cause the other, but it might not. So, Heideco, possibly, was interested to see if there was a relationship between what people earn and the age when they left education or training. So how much you earn against when you left education. So this is the age you leave full-time education, and this is how much hourly pay you get at age 25. So this shows that people who left education earlier are earning more money, because we've got a negative correlation, than people who left education later. She says her data supports the conclusion that more education causes people to earn a lower hourly rate of pay. So what we're asking for is, does one cause the other? Does this correlation, because it does show correlation, we've got an outlier there, but it does show negative correlation, does it mean that one causes the other? And of course, if you think about the situation, it's likely that lots of these people were still in education, hadn't had any work experience, perhaps are still in education. So even though at the moment they're earning less money than the people who left school earlier, the chances are that if this was an hourly pay at 25, at 30, at 40, at 50, then these would be earning significantly more money. Okay, so one isn't the cause of the other. They are correlated. Okay, this is from exercise 4A and it's question 5, so one less to do when it comes to practice. The table shows the daily total rainfall and daily total hours of sunshine in Lucas from a random sample of 11 days from the large data set. So we've got R representing the rainfall and we've got S representing the total hours of sunshine. So the median and the quartiles for the data are these. An outlier is defined as a value which lies either, well, we're used to this, aren't we, 1.5 times the interquartile range above the upper and below the lower. Show that R equals 21.7 is an outlier. Okay, so you can do that by finding your interquartile range, multiplying it by 1.5, adding it onto your upper quartile, and then showing that 21.7 comes out of that. So I've probably done that here. Yes, I have. So here are your calculations. You can work yours, pause the video and check it. Okay, good. Right, next one. It says, give a reason why you might include or exclude the day's readings. Well, you might include it because it's perfectly reasonable that there could have been that much rainfall. So there's no reason to believe that it's incorrect, but it is an outlier, so it might not be representative of typical rainfall. Those are the reasons I've put there. Then describe the correlation between rainfall and hours of sunshine. Okay. Hang on. Exclude this day's readings and draw a scatter diagram to represent the data for the remaining 10 days. Okay, if you can be bothered to do this, and I sort of did it, but I did it quite half-heartedly, they aren't perfect. All right, I put my points are not perfect. I was rushing. Don't do this. But I don't think you're going to be asked to be, that's showing some sort of negative correlation, isn't it? I don't think you're going to be asked to do that, but make sure you could draw a scatter graph if you wanted to. I'll tell you what I am going to do instead, just so I can teach you how to do it, is we're going to find the correlation coefficient, which is called the product moment correlation coefficient, which I'm going to teach you next lesson. I'm just going to show you quickly how we do that in our calculators. So get your calculator out, pause me if you need to, okay? Right, in your calculator, you want to go menu, 6, so that's your stats menu. So menu, then you're going to 6. And then you want to do the number 2, which is y equals a plus bx. I'll tell you about it why in a minute. I'm going to use this quite a lot. Then I want to enter in your R values for x. So 6.8, go along there. Don't enter them as pairs. Do all the x's first of all. Then when you've done all the x's, I just press the down button and it takes you right up to the top and you can go across and do all your y's. That's a quick way to do it than scrolling. So now I'm doing all my y's with an equals in between. Okay, so I've got all my values in now. So now I'm going to press option and I'm going to go to number 4, which says regression calculations. And I'll explain what the rest of it means later. But in there, you'll find this. R equals, is the third thing, minus 0.2937. Now, if you imagine that on the scale that we said at the beginning, minus 0.2937, it's going to be around about here. So there might be some very weak negative correlation, but it's not really showing much, is it, in the way of correlation? Look at my, let's go to the other one. Look at my diagram. I said it was sort of looking negative-y. Maybe if we took out that, I don't know, it's negative-y, but it's not great. Well, it's not. It's minus 0.975. Okay, so describe the correlation. Describe it, weak negative correlation. Do you think there's a causal relationship between the amount of rain and the hours of sunshine on a particular day? I've said yes, it could have a causal relationship. Because rain here on this axis, lots of rain means there's loads of clouds. And if there's loads of clouds, it's blocking out the sunshine. Okay, so I would say yes to that. Okay, right, moving straight on to linear regression then. And actually, keep up. You've probably still got your calculator in front of you from the last question. All right. Now, the last question, on your calculator screen, you've got 3 values. The last one was the R. Blah, blah, blah. All right. The first one you've got is A. The second one you've got is B. 1395. There we go. And right at the top, it says this. Top of your calculator screen. Now, that is the equation of a straight line. You know, y equals mx plus c. Okay. But it's written slightly different way round. Okay. So that's your constant. That's A. And this one, B, is your gradient. So instead of using M, we're using B. So if on my graph here, I did a least squares regression line, what you called a line of best fit at GCSE, if I drew that in perfectly, which I can't, but if I did, it would be the line, watch these go together, y equals that plus that or minus that times x. So it will be the line y equals 5.79 minus 0.1395x. That will be the equation of the regression line. Okay, so the way that a perfect regression line would look, hang on, I've got to let the dog out. Go, 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 go. Shut the door. The way that a perfect regression line would look would be if you took all the points above the line and you dropped a vertical down to the line, the sum of all these ones at the top would equal the sum of all these ones at the bottom. But you're never actually going to have to draw that in. So doing that thing we just did on our calculator tells us what the gradient is and tells us what the y-intercept is. So it gives us the equation of the line. And then you can use that to make predictions. Okay? So, where are we? That's what all of that says. A plus bx. And obviously, if your gradient is positive, that means it slopes that way. It would have positive correlation. If your gradient's negative, it would slope that way, so it would have negative correlation. And b, the gradient tells you the change in y for each change in x. Okay, example 1. How do we interpret the gradient of 3? Well, this is time spent revising versus the exam mark. So this 3 here would indicate for us, for every extra hour we spend revising, we're going to get 3 extra marks. So the change in y with respect to x. How y changes according to how x changes. Now, how do we interpret 20, this value here? Well, you could get 20 with no revision at all. So there's your 0 revision, and you still get 20 marks. Okay? Now, what I want you to do is I want you to pause the video and I want you to try this example 2, and then we're going to go through the answers. Okay, welcome back. So, for example 2, excuse the not pointing, but my pen is just charging up. So just give it enough to finish off the rest of this. So the data was plotted on a scatter diagram. Now, what's actually probably going to happen in reality is they're not going to plot the diagram for you. It's much more likely that you're going to enter W and G into your calculator and bring out the regression line yourself or the correlation coefficient. Okay, so describe the correlation. Well, you can see from the diagram it's got a strong positive correlation. It gives us the equation of the regression line and asks us to interpret what the gradient means. So each time the wind speed increases by 1 knot, the maximum gust increases by about 1.8 knots. Or you could multiply that by 10 and say each time the wind speed increases by 10 knots, the maximum gust increases by about 18 knots. And C is interesting and often comes up. Justify the use of a linear regression line in this instance. So the correlation suggests there is a linear relationship between G and W, so a regression line is suitable. So you could say the points pretty much are forming a line, so therefore we can use a regression line as a suitable model. Okay, next bit. Oh, gave you all the answers for that anyway. Okay, interpolating and extrapolating. So interpolating, we've talked about this before, interpolating is working within the data, making predictions, but it's within that set of data that you've already had. Extrapolating is going outside of the data, and you've always got to be aware of extrapolating. So here's an example. So this was yesterday, 0 husbands. Today, 1 husband. So that means that in 4 days, I might have 6 husbands. Okay, as you can see, by late next month, you'll have over 4 dozen husbands. Okay, better get a bulk rate on wedding cake. So, extrapolating, must be careful. Right, so, it can be done, but you would always beware. So, interpolation, extrapolation. So, example. So, this is the head circumference and gestation period, X weeks of a random sample of 8 newborn babies at a clinic are recorded. The scatter graph shows the results. We have the equation of the regression line and it is used to estimate the head circumference of a baby born at 39 weeks and a baby born at 30 weeks. So it might ask you for those estimates. So at 39 weeks, if you go up on 39 weeks gestation on the x-axis, so that's here, that's within our set of data. So that's perfectly fine. That would bring out, we could use that to predict. Whereas a baby born at 30 weeks would be here, and we've got no data at this point. Okay, so, that's the wrong one. So the prediction for 39 weeks is within the range of data, so therefore it's likely to be correct. The prediction for 30 weeks is outside the range of the data, so it's less likely to be accurate. And for the last part of the question, a nurse wants to estimate the gestation period for a baby born with a head circumference of 31.6. Now that looks like it wouldn't be a problem because it's within our range of data, it would come here. But it's not suitable because this is the independent variable and this is the dependent variable. Yeah, so the gestation period can read off the head circumference, but the head circumference can't read off the gestation period. So the independent variable is x, the gestation period. You should not use this to predict a value of x for a given value of y. So you mustn't predict x from y, you can predict y from x. Okay, that was the whole chapter. Good, we've done a brilliant job of that because we've finished. So exercise 4A, 4B, mixed exercise 4. If I were you, I'll go straight to there and pick out a few questions that look good. Okay, now the stuff I taught you about the PMCC, when I told you how to put it in your calculator, and your value of R, actually just saves us a little bit of time next time when we actually will need that when we slip straight into the book 2.